Anyway, hi everyone. My name is Shlomo. I'm a member of the MySQL infrastructure team at Facebook. At Facebook, we have multiple teams that work with MySQL databases. The first one of which is MySQL database engineering. They hack on MySQL itself, make various changes to the code base, maintain the server. We have our performance team, which are the closest thing we have to DBAs at Facebook. And we have our team, MySQL infrastructure, which is responsible for doing all the maintenance work on all of our automation, writing automation, and creating systems that maintain and run the site as is. So before joining Facebook in 2011, I used to work on MySQL for multiple years, since about 2006. And before that, I used to work on SQL Server, believe it or not. Microsoft makes databases as well. It was about since 2002. So I've been working databases for quite a while. So I'm going to talk to you about a bunch of things. So this talk is going to be a nice description about how our automation works and how we do things at Facebook. And also, some of it is going to be like historical things that show how a company that started off with a small amount of databases have evolved to be able to maintain a huge install base. So I'm going to describe a bunch of stuff. First one is our architecture, so you kind of know what you're dealing with when you're talking about something of our scale. Some automation building blocks, a system called MPS that allows us to scale ourselves and our work to be able to be very productive and not do a lot of work most of the time. And mention some challenges and how we solve them, and finish up with some war stories. So let's get started. Let's talk about how we run MySQL. So this cube you see here is a server. We run our, I know it doesn't look like much. So at Facebook, we actually run our databases on actual hardware. We don't use any layers of virtualization. And we run more than one MySQL database on a server. And we have multiple instances. That's how we call them. Some people might call them something else. This is just a MySQL database that runs on a specific port. We don't use any zones or any other fancy thing. It's just run on different ports. On an instance, we allocate data into MySQL databases that we prefer to call them shards, since it simplifies naming. Shard is more unique database. Everything is database. So shards just MySQL schemas on top of these instances. And for the most part, for our largest systems, we allocate data in a static manner to these shards, which is a pretty classic thing to do. So if you're a Facebook user, your data is probably going to be allocated to a specific shard, and every shard gets a certain range of users, and so on. So it's pretty simple. So I'm going to use this diagram going forward for some of the explanations. And for the most part, we mostly care about one of the instances, since most of the concepts that are logical deal with that. So our machines do not exist by themselves. We run a replication. We don't just run one host, of course. And we use vanilla MySQL replication. It's currently statement-based, which works pretty well for us. So for those that are not very familiar with MySQL, the master is the node in the replication, or the replica in the replication, that gets all the writes, and these are called slaves. If you want to be more politically correct, you can call them replicas. It doesn't matter. We just call them slaves, as in the normal MySQL terminology. And the entire thing, the entire thing is called, pardon me, my slides got ahead of me. Amazing. I'll stop using the remote. Anyway, master, slave, and a replica set. There you go. Replica set is a word we made up to describe this compilation of master and slaves, since it's an entity that we really deeply care about. And since the machines can share installation at the same host, so this specific instance here can be used by multiple different replicas. So in green, you can see that this same machine can be a master for one of the instances, and for the other one, it can be a slave. Sometimes people have different hardware for their installation. So, for example, sometimes you keep slaves as flash and the masters as disks and weird things like that. We don't do that. We provision all of our machines to be able to run both. So this is a very much possible configuration. We don't worry too much about this stuff. And next thing is a promotion. A promotion is a more positive way to say failover. And nothing is failing, it's just a promotion, things are getting better. So promotion is when we change the active master of a replica set to be something else. Another common scenario that might occur is an actual failure. If one of your replicas dies for some reason, and we need to replace it. So in that case, we bring in another machine from somewhere else. We call those machines a spare. And an operation where you replace a machine, we call it a replacement, as one might guess. So how do we do that? After we get another host that is going to replace this machine, we copy data from one of the members of the replica set. It could be a master, could be a slave, it doesn't matter. We perform a copy from the same host. I mentioned this specifically since some companies like to restore from backups. Some run MySQL on shared disks via NFS or DRDB, various things like that. This is what we do. We perform a copy. I'm going to mention in a bit how that copy works. And after the copy is finished, everything goes back to normal. So a quick recap of the terminology. We have server. Server contains multiple instances. Instances contain shards. We have replica sets that have masters and slaves in them. We have promotions or failovers, and replacements that require a spare. So before I continue, I'd like to stop for a second, and this is the historical part here. When I joined Facebook in 2011, the higher level automation that exists today did not really exist. It was in very early stages. And regardless of what higher level automation you write, you need to have some things in place. And these things exist in every company that runs MySQL at any scale. And it just depends how complex it is or how well developed. So the first thing is inventory management. So this exists in every company. Like even if you don't realize you have inventory management, maybe you're using AWS and does it for you. Maybe you have an Excel spreadsheet, maybe you have a file somewhere. It depends on how many people you are, but you still have something like that. At Facebook, we have a system. It has complete inventory. It's a pretty amazing and comprehensive inventory. Even they know everything about every server, about every rack, every MAC address, and every server, almost up to the bolt level. It's pretty amazing. It's very comprehensive, and the most important thing is that it contains an API, so we can query it from our code. So this is our source of truth when thinking about the hardware we have in space. Second thing that, again, exists in almost every company that runs MySQL is a directory service. For us, this maps for the logical layer, it maps the logical layer from a shard name to the replica that something is located in, to the list of instances that can serve this data. Some companies, again, might use DNS for that, or some other solutions, failover, AJ, MySQL Heartbeat, various systems that move data around. Our system is based on Apache Zookeeper. I say base because it's probably we only use that as a storage layer, so we have a lot of things built on top of that. Provides very low latency and has a lot of MySQL specific support. So, for example, it wouldn't allow us to have two masters in the same replica set and things like that. It has various sanity checks. And it is the specific, it is the source of truth for everything and where it's located. And later on in the war stories, I'll show you why that can be, sometimes can, you can shoot your own food basically, but I'll get there later. Automated provisioning. The level at which it is automated can vary between different companies. At a previous place I worked in, there was a guy that did all the automation, all the provisioning, so that was the scale of automation. You ask him to do it and he does it. It was very simple. Facebook, there's too many machines to have a guy that does that. So we have a system that's called Cyborg, and it provisions a machine. It's of course, it's more complicated than the command here, but it is as easy as that to take a machine and reprovision it from scratch. It does it at scale, meaning it can reprovision thousands of machines at the same time. It manages repairs. Since we're dealing with actual hardware, not virtual machines, as DBAs, we need to be aware of things like that. We can't just like throw away a VM and get back a different one. We have to actually think about this stuff. So machines go into repair, and we need to know that they're there. And it uses Chef internally. We used to use CF Engine, and we migrated a long time ago. Next thing, automated promotions. That promotion I mentioned before, it's those of you who work with MySQL know that promotions are really hard to do, right? And they're kind of hard to automate. We got to a point where we have a single command to run a promotion. It's great. It runs very quickly and with very low downtime. P99 is like 5 seconds. I think it's even lower now. So that's great. Next, replica creation. Regardless of how you do this, if you work with MySQL, you need a way to build out slaves. It could be MySQL dump. It could be taking snapshots of your file system. Whatever way you choose, bringing a host down, whatever way you choose, you need to have some way. The way we do it, we have a custom version of Extra Backup. And we copy from one of the hosts in the replica set, like I showed before, and then we create a new copy, straightforward as that. And our tool not only creates a new replica, it also makes sure everything is connected, it does various validations. And the final one is central resource locking. This actually, we didn't think we would need that. But when we started writing automations, it would be fancier and smarter, but we still had humans meddling around. Apparently, automation and people can step on each other's toes, do things at the same time. So we wrote a system that would allow us to prevent that from happening. And we didn't do anything too complicated. We basically use a MySQL database and a MySQL table and some queries on top of it. I mean, we're all DBAs, so we know how to do that stuff. That's pretty straightforward. So it's just a database. One of the my main points here are going to be that try to keep things simple if you can, and not overcomplicate it if you can avoid it. So this is one of them. We didn't use any fancy distributed locking system, and somehow it still works. So, quick recap. Inventory management system, directory service, automated provisioning, automated promotions, fast creation of new replicas, and central resource locking. All of these things, for the most part, in whatever iteration, they were in place around 2011 before we started working on a system called MPS, MySQL Pool Scanner. I'll mention later why it's called like that. It's actually a weird name. But why did we start working on the system? What prompted us to do that? Well, as the amount of servers grew, we needed one thing the most. We wanted to get some sleep. You can't do this manual work nonstop, even though we had people that used to do 24-hour shifts. Yeah. Some of them are here with us in the audience. It doesn't scale. You can't have humans doing all this work manually. So we decided that we're going to somehow make something a bit smarter. So the first thing we did is think about what does a server's lifecycle look like at Facebook? Or actually, it's in every other company. It's very similar, but this is how we think about it. So a server starts its life in their image state or in the provisioning state. And then if it's OK, and if it exited as a healthy server, you can put it in a pool called the spare pool. Makes sense. Then you can allocate these spares, like I've shown you guys before, and then a spare will be allocated while it's being consumed, used, and if everything is fine and the copy succeeded, the machine goes into production, and then it's a production machine for all intents and purposes. If a copy has failed, then, well, who knows why it failed. We move it to a triaging state called spare deallocated. If the machine is fine, if it goes back into spares, but if it was broken and the health checks failed because the machine died in the middle, it happens, machines die, then we just send it back to Cyborg, which will decide what to do with it. And if a machine is in production, it can go mostly two places. Either we remove it from production, and then it goes back into spare deallocated, or we replace it and put it into the drain state, which means that we want to keep it somewhere in this limbo so no one touches it. For example, if you allocate machines for testing, if you need like 200 machines to do something with them for some reason, or you want to move the racks around or things like that. So we have this state for this purpose. But this mostly covers the entirety of what a machine goes through in its life. And then once we had that in place, we could write a system that would express these different things and automate the work one might do around it. So you can imagine that the transitions between these states are a bit more complex than what I'm describing. There are many different factors here. And writing all this into code would be kind of hard and not scale very well, and you might need to change that while the system is live for various reasons. So we decided we're going to be a bit more fancier here. So we defined the concept we call a problem. It's not really a problem. You can think about it as a tag. Basically, this is a tag that's associated with an instance, and then it maps from a specific state and the problem the instance is having to a specific action and the final state. And this can express most state transitions we wouldn't do between these different states. And just for clarity, since this is defined on an instance, if for a specific host, if you want to know if a host has a specific problem, you just assume that if all instances have this problem, the host has this problem. So example number one, if you have a full disk. So a machine is in production, has a full disk, you want to replace the host if it's experiencing this problem and put it into spare deallocated. Of course, once it's in spare deallocated, you don't want to do anything wrong with it. You just want to clean it up and put it back into spares, because the machine is fine. It might have had multiple instances on it, and you removed one. Now the other one has enough space. That's it. You're done. So, and you can reuse this instance, maybe for a smaller one. So this handles this case pretty well. And a different occasion, although it looks kind of similar, is if you have a RAID issue. So if you're in production, you have a bad RAID card, you want to still replace the instance and send it into spare deallocated. But once it's in spare deallocated, the system is going to see that it has this specific issue, meaning it probably needs to go into repair. So it's going to just move the instance into the reimage state, and eventually it's going to be taken care of, again, by our repair systems. So it's very similar, but the nuances make it easier to understand. So this case is a bit more complicated. When we run MySQL, we often want to run the latest version. So we upgrade it fairly often. We actually have a pretty good cadence of upgrades. Our engineering team, hands off, release probably every quarter or more frequently, and we try to upgrade as frequently as we can, which is quite great, by the way, for having worked in different places where you can't be on the latest one that often. So I'm quite happy about that. So if a machine is in production and it's running an old version of MySQL, usually don't want to do anything because we do upgrades out of band. We have a different system that does it carefully so that no downtime is going to be experienced. But the system, MPS, is great for mopping up, meaning if something is left somewhere in a weird state, we're going to take care of it. So if a machine passes through spare deallocated with an old version of MySQL, we're going to just replace the entire machine and make sure it gets reprovisioned and gets a new version of MySQL. And that makes things pretty easy. And if a machine is in spares, has this version that we've decided to blacklist, it's also going to be cleaned up. So if for some reason machine was in a weird state somewhere, got brought back into the spare state, it's going to be cleaned up. So it's pretty expressive and it handles most of the cases. So I'm going to talk about how the system actually looks. How do we express all these states? How we built the system that transfers things between them. So the first thing we have is, it's very meta, a metadata database. It contains data in the database. It's metadata. It's data about the instances we have, about the servers they live on, and the various copy operations that happen. So instances meaning the instance I described before, but it doesn't just contain a list of them. It contains various information about them, such as what version of MySQL they run on, what problems are they having, right? These states have to be, what state they're in, things like that. Servers, we know everything about their hardware because we have lots of different machines, depending on the time of year, but we have lots of different machines. And we need to know how much memory they have, how much disk space, and so on. And it also contains various queues and the system for which we manage the copy operations. And we store a bunch of modern configuration data in Zookeeper because not everything belongs on the database, surprisingly. But yeah, that's pretty much it. Next is local triage. The agent that is MPS uses. So it's called local triage because previously it used to only do triaging for the local host. The names are not very creative. It's an agent that runs on every machine every few minutes in a cron job and maintains all this metadata in the database. It makes sure that the machine is registered there. And I have a slide specifically that explains how awesome it is in a very practical example, and that's a bit later. And it also raises these problems that you can see. You can inject problems by yourself, or you can have this automated system raise these problems. It also does various things like proactive detection of various problems. For example, we had an issue where disks would stall sometimes for a specific amount of time, and you can't just detect it easily. So someone wrote some code in Python that would detect this, scan various log files, and so on. So this is our tool that allows us to do that across the entire fleet. Next is the actual system. And this might surprise some, but the way we do this is we have cron jobs that run every one of these states. We just execute this Python file with all this logic inside, and we just execute it every few minutes, and it processes the state that we want to process. It's very, very simple. It's very easy to move crons around. It's very easy to debug. We didn't build a daemon because we didn't need to. It works surprisingly well. So we have a state for every single state that we need to process in that map that moved between states. So we have a cron line for every one of them. And these are production, spared, dedicated, and so on. And we have a specific part of the system, again, that's implemented in a very similar way that moves things between various states of the copy process. I'm not going to go into these in depth because I have some information about how copies work later on. And the latest component is the command line utility. We need some way to control it. And if you notice from that slide, the database is in the middle, but everything else is around it. These components don't talk to each other. They communicate through the database. So we have this command line utility that allows us to extract data from the database and sometimes from servers themselves. It will tell you what the status of a machine is, status of a tier. If you have hundreds, thousands of machines in a tier, you can look at that. Drain a host, allocate a machine if you want to get it for testing, replace a host that you think is malfunctioning, do lots of maintenance work, check how copies are going, stuff like that. And here's an example of a command you can run with MPS. You can say, MPS, what is the status of this specific shard? And it will tell you this shard is actually our database that contains data about, this is the metadata database shard. So this is the information about this specific one. You can also say MPS replace this machine, and it will replace the instance. The reason I specified here is demonstration. It immediately comes back with, yeah, I've marked this for replacement, I got this. But if you ask it about it right away, it would say, well, I don't really know where I'm replacing it from, where I'm copying this instance to. It has no idea what's going on because it's in the pending state, meaning nothing has happened yet. It's going back to what I said before, we run in state, so if I run this immediately afterwards, that state, that process is pending, which actually makes a machine, makes a copy job be initiated, hasn't run yet. So it's kind of decoupled. And the reason why it's not a problem is because if a copy takes multiple hours, it doesn't matter if you kick it off in 1 minute or 4 minutes or 10 minutes, it doesn't really have a big impact on the end result. So replacements. Replacing a machine is actually very hard. There's a lot of work that goes into that. First of all, before you start copying something, you need to decide where you're going to copy it from and where you're going to copy it to, and these are difficult choices to make. And I'm going to explain in a different set of slides why it's actually interesting. So once you've decided where to copy something from, it's also a good question because sometimes you need to think where you're going to copy the data to. So maybe it's a different data center. Maybe it's a slower machine. Maybe this machine is currently having a specific problem, so you wouldn't copy from it. There's a lot of things to take into account. So once you decide where you copy from and where you're copying it to, you can initialize the copy. This is before you even started. Once it's going, you need to monitor it. You need to make sure everything is running. You need to make sure the machines haven't died, and you don't need to send them back to Cyborg to deal with them. And after a copy is done, you need to make sure everything went fine, right? You need to productionalize it, meaning marking various checkboxes that say this machine is now in production. And you also need to do some cleanup. For example, if you've done a replacement, you need to delete the old replica. So this is why picking a destination is hard. So this is a very interesting slide, and I'm gonna try and explain this, and raise your hands later if I have not explained it sufficiently. So the vertical lines are stacked instances. So the different colors on this graph represent different instances. The very light blue color is for port 3306. The darker colors, the gray and the dark blue, are 3307 and 3308. And the dark line at the top is just the maximum amount of space you can pack in a machine. So this is a location map of one of our data centers from a while back. It contains multiple different generations of machines, as you can see. And I could get this thing by the PR department because you can't really know how many servers we have. Because the maximum resolution on the screen is 1080p. But there are way more servers here than that. This is a sampled version. So you know we have at least 1,000 machines. And this is how they're allocated. So as you can tell, like, allocating this is kind of hard. And our goal is to have even an efficient server utilization. Like the way this graph looks now, it's pretty great. All of our servers are mostly used. Apart from these ones on the rightmost side, as you can see, we're not using all of the space on them. If you're wondering why, it's because they're just not fast enough and we artificially limit them. Otherwise, disk space kind of correlates with performance for us. It's a common question. So how do we do that? How do we allocate hardware quite efficiently? So actually doing this perfectly is a variation of the bin packing problem. If you ever had to deal with something similar, it's not that easy. So we decided not to go all CS on it, so we just have a greedy algorithm, which is actually good enough. It's probably about, like, according to various papers online, the greedy algorithm is about 13% worse or something like that. Anyway, it's good enough for us, and this is how it works. So first we need to decide how much we want to fill up machines. So it varies between different tiers depending on how packed they are. Basically, we want to eliminate the standard deviation. So we want to pack machines kind of tighter to each other so they're all mostly similar in the amount of space. So we decide on a target percentage of how much a host should be full. We do that by calculating the median utilization of an instance and then multiplying it by the number of instances per host. So use an example. If you have, usually an instance takes about 35% of the size of a machine, then if you have two instances per machine, then essentially you want to fill up your machines up to 70%. And that is quite a good number most of the time. And it varies according to how much the tier is full and so on. We don't need to manage any specific configuration for that. Then you find the spare instances. And you project the future utilization for the hosts that these instances live on according to what it would be if you had copied a source to that, your source of copy to that destination. And you calculate distances in percentage, and you pick the one with the smallest distance. So basically, if you could find the perfect match that would be as close as possible to your desired target, jackpot. And if this happened every time, our graphs would be completely flat. Instead, they're like this nice curve. And this works quite well. And here are some pretty graphs for you. So the graph on the top is quite interesting. So we run some tiers up to 8 machines. Up to 8 instances per host, and this way we get more color variation. This is the main reason we do that. So the reason why it's not completely packed and you have some of this long tail on the left side is because this is actually multiple data centers in the same graph, and there's some inefficiency in every data center because allocation is per data center, but it looks nicer when I look at all of them at the same time. So it's nicely packed, very equal, it works great. And the one on the bottom is a different data center, different tier. Again, it doesn't tell you more than the fact we have more than 1,000 machines. Yes, as you can see, it's pretty well balanced. So I like to look at those graphs. It makes me happy. So here are a few examples of how this automation makes things very easy for us and how it makes our lives much easier. The first thing is turning up new servers. And if you guys are lucky enough to be working with AWS exclusively, it's not a concern for you. If you have actual physical hardware, you probably know how painful this is if it's not completely automated. And at Facebook, this has been done quite amazingly well. Most of the layers that build up to that are not even ours. But basically, people roll in new racks. These are actual racks of ours from the Open Compute project. This is a picture from the Facebook page of the Luleå data center in Sweden. These are actually our machines. So these racks roll into the data center. They get plugged into electricity. All our inventory systems know what they are. They automatically get provisioned. All their data about every single piece of information is registered, and they just show up in the system. Next, Cyborg comes, provisions all of them, makes sure they're fine. The ones that are broken get sent into repairs, techs go, examine, fix them. We don't do anything at this point. Then our directory service comes. Because Chef installers everything on these machines, they wake up and they already know how to find our metadata database. So they can locate it easily, and then they can connect to it and tell this database and our systems in turn, say, hey, I'm this machine. I just woke up in a data center. I have no idea who I am, but this is my name. I think I should be doing database work. And automation says, no problem. We're going to put you into the spare pool. You're going to be ready for production. So it ends up being super easy. These racks show up. We don't need to be notified. So one day you come into the office and you look at the dashboards and you suddenly see you have 1,000 more servers. We've done nothing to do that. It's great. It didn't used to be like that. And again, since we're dealing with actual hardware, we have various maintenance operations. And one of these things is moving racks between different clusters. Clusters are physical entities. We need to sometimes drain machines, make sure no one uses them. So it used to be a manual operation. If you need to move something away from a machine, some of the techs say put something elsewhere, stop using this, or these servers have problems of various reasons. We have one command that does this now. We have one command. It's integrated with our task management system. So when it's done, it can tell you I'm done, and you can pass the task along and say, hey, it's done. Very low friction. And we can even decommission full clusters like that. You can say decommission the whole cluster. And since MPS is kind of clever, it knows where everything is. It understands which cluster machine are in. It's going to look at all the machines there, run a replacement operation for every single one using the same algorithm that I described earlier. And now suddenly you have this work being done for you. You don't need to dedicate people to do this work anymore. It used to be someone's job to do this. And this is a good example. When you want to build out a new data center, you want to set up a new data center somewhere. We've done this multiple times in the last few years. So previously, the first time we did this, in 2011, I remember it was someone's job for 3 months. He had to dedicate, he would come into the office every day and make sure everything is fine, copy. We had some nice automation that would actually build out servers automatically. But it still needed a human to look at it. Now we change the configuration option, and then the system just goes out and builds a new data center. Yeah, I can't say how much. But it's pretty fast. Other interesting examples are, for example, how do we do major Linux version upgrades? So we just tell MPS to take care of it. We don't need to worry about it because everything comes out from the provisioning system in a clean state. And one of the great things about this is that if you work with web servers or whatever, you can just have Chef reprovision them, get a bunch of new ones reprovisioned. You don't need to worry about data. These are all stateful systems. There's a lot of work that goes on in the background to move data around to make sure this is so easy. So you can just say your image is host or image is rack if it has whatever issues. And you can also tell MPS, so if you see this old version of a kernel, mark this as a bad version and mop up the same way it would do for any MySQL installation that has been blacklisted. If we do maintenance on rack switches, we can tell MPS to ban this rack from being masters, so nothing is going to be promoted to it. And if something is a slave, it's going to be automatically disabled in case network is lost, so it's not a problem. So that makes it quite easy. And MySQL Arbor, as I mentioned, is an out-of-band process that we run automatically most of the time, but we use MPS to mop up. Now the best part, war stories. So the first one is, I call it the case of the helpful janitor. MPS is a very good system. It likes to help us. It does everything automatically. But we had a bug. Remember this directory service? So there was a bug in the servers that corrupted the data. And it ended up basically marking a whole replica set as not being in production. So MPS trusts the source of truth. You have a source of truth. It has to speak truth. And when it has some corruption, MPS says, well, I don't know what this machine is. I'm going to help you. I'm going to clean things up. So it waited for a few hours because this machine used to be in production, but it's not sure. And then it decided to just delete everything. Very efficiently, because it didn't delete just one machine, deleted all of the machines in the replica set, and very quickly. So we had to restore from backups, which, of course, we have. We have backups. We have backups for everything. It works great. So now we have a temporary holding state. Now MPS does not trust the source of truth as much. It will say, well, something here is fishy. It's going to put it into a holding state and ask a human to look at it. It will send alarms and nag us so that this would not happen again, ever. Next bug, or sorry, a war story. Replace all the things. So there was a bug in the hardware fault detection library, and I'll explain what that means. We have a library we use that looks at the host and says, oh, this machine has some hardware problem. So someone pushed a new version of the library. The library is actually detecting yet another issue now, so it's smarter. But this time it failed for some reason on our machines, and specifically on one generation of our machines. And MPS said, oh, all of these machines, they're all broken. I'm going to start copying everything. And the funny thing is, the machines that were broken were in one data center, broken, right? They were fine. And they were in one data center, and then all the machines were the best candidates for a copy since they were free and they were fast and capacious. They were in different data center, and this is what happened to the network. Basically, our very new and fast data center completely obliterated the old one, just crushed it. The more you look at that GIF, the funnier it gets, honestly. So we decided we can't let that happen again. So we now have various hard concurrency limits, so you wouldn't copy too many things at the same time. MPS is also much more suspicious. So if the same problem appears on all the machines, it says, wait. This was way too fast. I don't know what's going on here, but I think something is wrong. It's going to call a responsible adult, which is one of us. And this should not happen anymore. It hasn't. We also now stage our releases, meaning that something like this would get rolled out gradually, and we would probably notice this from various alarms and so on. So, problem solved. Next, prepare for takeoff story. It's my favorite. Okay, this is another hardware-related case. So, does everyone know what BMC is? So BMC is base motherboard controller or base something controller. I forget what the M stands for. This is the controller that says things like your fan is supposed to run a specific speed, your temperature is this, like do various very basic things on your server. So this hardware fault detection library decided that some of our machines, their BMC was in a bad place. It was having some issue, and honestly, it did have some issue. So the guys at the team said, well, we can just restart the BMC. It should be fine. Like, okay, we roll out a restart for the BMC controller, and everything was fine. All of our alarms went away. There were no problems, and everything is great. So, and everything was fine for probably about 45 minutes, and then we got a call from SiteOps. SiteOps, for context, never call us. SiteOps are the guys that are in the data center. They never should call anyone. Like, we have a way to communicate with them. This is very unusual, and the guys call us and say, well, we have some issue here. The power consumption data center increased by 1% or 2%. We can't walk into the database suite because it's too noisy in there. It sounds like a 747 landed in there. And we can't go in there without hearing protection. And also, there's a fire truck on site. So, what happened? So, this is so weird. So basically what happened is that once we ran the reset for all the BMC controllers, there was another bug, of course, which made all the fans in all these machines run at full speed. So you can imagine it was very noisy. It consumed a lot of power, which explains all the previous things, but why are the fire trucks? Well, these fans were not spinning very fast before that, and once they've been all spun up to full speed, they kicked off a lot of dust into the air. And our systems that detect fire, they decided that there was too much dust in the air, and it's probably because something is burning. So the local fire department was summoned. True story. So as a summary, automation gives us great tools to shoot ourselves in the foot as much as we want. And this is one of my favorite quotes about that. And it's, I see everyone has read it at this point. Yeah, so since it gives you too many tools to do things right, it also can do a lot of mistakes when it goes crazy. So whenever you design any type of system that deals with any large amount of hardware, or machines in general, even if they're virtual, it's fun to think what kind of damage you could cause if you let automation run amok. And one of my favorite things is that, specifically at Facebook, whenever you deal with this amount of machines, it often has implications in the physical world, which is quite unusual, I think, at least for previous places I worked in. So I find that kind of awesome. And before I wrap up, I'd like to mention a specific tool we have. This is a very common question that people often ask. How do we do real-time remediation? So I have not covered any of that. Everything I've talked about was systems that run in the background and basically replace humans. We have a system called dbStatus, and this is our real-time agent. It does all sorts of fancy things that replace Nagios for us for a much faster and more reliable alternative. It does alarming. It does fast failure detection, failover, promotions. It has replication heartbeat and various other interesting features like making sure that our really log partitions are not getting filled up. And it also would disable machines that are bad and so on. So if you want to know more about this tool, you're welcome to visit our booth. You can ask Nathan about this. He wrote the damn thing. And that's all. Any questions? Questions, anyone?
I don't know if you covered this, but how do you guys detect replication failures with MySQL? And then how do you automatically react to it? Or is that something a human has to?
So it depends on what type of replication failure. Some of them can be auto-remediated. So some of them can't be. You just need to wait. For example, if we have a slave that's lagging, we have a way to disable that slave so that nothing is going to access it. So we'll know about that. There are some cases where, for example, we know that restarting the IO thread is going to make things better. So we have automation that detects a specific condition, and we'll do that. And reconnect, for example, if it's caused by a slow network or various weird issues like that. And if there is a replication failure that's impossible to recover, we'll just replace the machine. We have a very big hammer called the replacement to just can fix any problem like that.
Yeah. Hi, you mentioned that you had one cron job per state. Could you drill down on that? Like, you mean each cron job would go through all the machines in a particular state and process
Yeah.
them? But you're dealing with the error had the two components, the state and what the
Copy operations.
right. So isn't that event driven? Don't you need to deal with things as the event comes in, or are you processing the events for machines in that state?
So events don't really come in. Every time you run, you look at everything in that state, and that's surprisingly quick because computers are quick. So it's never been an issue that it's become slow. And you just see if anything has popped up that requires action. So for normal state management, so we have state and we have the copy management. So I'm talking about state right now. So you look at machine-specific state. If there's no problems that require actions, there's nothing for MPS to do.
Okay, so the problems queue up, and the cron jobs are dealing with all the problems related to machines in that state at that time.
Yeah,
Okay.
the agent would run on those machines, and then it would bring up a problem and tag this machine. Then it runs and says, oh, do I have a machine with a specific tag? I should do something about it. Otherwise, it can just ignore it.
Okay, so did you do that so it avoids dealing with, I guess, locking and a lot of other issues, or?
MPS runs on only one machine, pretty much. You can move it different places, but it runs on one host most of the time.
Okay.
Yeah, we don't have locking issues because it's pretty much like a singleton.
Right. Okay, thank you.
Yeah.
Question.
Yeah.
So how do you deal with schema versioning?
Schema versioning. Okay, we have a separate system called OSC, online schema change. I think the major component of it is actually open sourced. And we have a system called AOSC, Automatic OSC, that deploys schema automatically. And you actually can ask this guy here, Istvan, you can ask him about that in length. He knows it pretty well. If you like more technical details.
Do you use the same provisioning and inventory system for front-end web servers and caching servers or and load balancers? I was wondering how you approach that.
Yeah.
Okay.
It's a Facebook-wide system. Like we, as the MySQL infrastructure team, we have not written these components. We write some parts that regard to what we do, but these are Facebook-wide systems that allow us to do things very easily. We're standing on the shoulders of giants, pretty much.
Okay, thanks.
Hi.
Hey.
MySQL does the static memory allocation for buffer pool. How do you determine the size of memory required per instance?
It's an excellent question. We do not. We just, if we have a machine that runs two instances, we dedicate every one of them to consume half. We're looking into having buffer pool that we can change in the very near future, actually. But right now, we just allocate it statically. So there is some inefficiency there, if you're wondering about that.
Yeah.
Yeah, there is.
Another question is, how do you deal with scenarios when master performance starts degrading? Like, for example, the master got a little bit unlucky and got on a really busy host, and it starts to slow down, which basically reflects on the slowdown of the slaves, and that's a pretty tricky thing to discover. And like that's one of the things we had in the past is like, I would say the failures are easy to detect, but the performance degradation is a little bit more challenging, especially on the masters.
So usually we have a whole team that deals with this stuff, and they usually notice this. Whenever something happens at Facebook, it's not just one master that goes crazy. Even if it's the 10th of a percent, it's already like lots of machines. So it can't be something very small. And for the most part, for the tiers that are the biggest ones, it's actually so well optimized that these cases has been resolved mostly years ago. And we provision our machines and we buy machines to a spec that would be able to absorb the traffic we experience. So this is not a problem. And for cases where you have smaller tiers with these issues, then it's a case-by-case basis. I'm not sure how I can tie it into automation. Maybe I didn't understand the question well.
Yeah.
Yeah.
No, well, you understood it right. So, okay, thank you.
Yeah, no problem. Any other questions? Viewer? That's all. All right. Thank you.